So yes, now we are again back on the road. So now we have here, for example, a rock sample, and we have more normalized trace element variation diagram for typical Iceland arc and oceanic island basalt. Yeah. So and there we are comparing the rock sample with MORB. So and the upper curve is the alkalic ocean island basalt. And below we have the Iceland arc alkaline basalt. So when the horizontal line at 1, that is the MORB, yeah, because we have normalized this with MORB. That means you are calculating this with a distribution coefficient, yeah, or you are taking the strontium concentration, for example, of your alkalic ocean island basalt and dividing it by the strontium concentration of MORB, yeah. So and the same for all the other minerals, and of course MORB has then a horizontal line, and the ocean island basalt and the Iceland arc alkaline basalt has its own pattern, and then you can make not make assumptions, you can say which elements, which incompatible elements are enriched compared to MORB. Now not compared to the chondrite as before. Now we are comparing it with MORB, and then you can say which incompatible elements are enriched and which incompatible elements are depleted compared to MORB, and then you can investigate what's the reason for that, yeah. So then we have at the top we have a normal function, that is this distribution coefficient, yeah. So here, for example, between iron and magnesium in olivine, yeah. I mean, you can analyze the mineral olivine, and then you get the weight percentage of magnesium inside and iron inside, and then the iron-magnesium ratio in your residual melt will change as well, yeah, because you are removing this. And this is for all the elements, and all these ratios are always changing during fractionation, crystallization, and differentiation, as well as assimilation processes, yeah. So fractionation, that is just you are forming a crystal and removing it from the melt. The differentiation process is a gravity process, yeah, that follows the Stokes law, and that means minerals which are formed, which has a higher density as the surrounding melt, like the orgite, is sinking to the ground of a magma chamber, whereas minerals like an anortite-rich plagioclase, which has a lower density compared to surrounding melt, will float up, yeah? So, and therefore always the ratios of those elements in these minerals which are formed changing, and therefore the ratio in the residual melt is also changing. So then we have the assimilation process, that is just if you have some interaction with some xenolites falling inside your melt, yeah, some other material from the surrounding area is falling in your melt by tectonic movements, or I don't know. So, and then this material becomes remolten. Then you are changing also again the chemical composition. So, and the fractionation process is then also temperature dependent, because at high temperature at the beginning you are forming a more magnesium-rich olivine. When your melt becomes cooler, then you are forming a more iron-rich olivine. The same for the pyroxenes, and for the clinopyroxenes and the orthopyroxenes. And for the plagioclases, at the beginning, at higher temperatures, you have a more anode-hydride plagioclase, which shows high calcium concentrations, and later on your plagioclase becoming more sodium enriched. So, and therefore your crystal lattice or your incompatible elements are always more enriched in residual melts, whereas the compatible elements becoming picked up very early in the melt, yeah. So, in these incompatible elements, they are hosted also within different minerals. So now we are coming to the next thing here, that is the radiometric methods using isotopes. So, and these are then the radiogenic isotopes. And here we have, for example, the rubidium-strontium method, yeah? So we have initially 4,500 million years ago, we have an 86 strontium, 87 to 86 strontium ratio of about 0.7, yeah? So, and this ratio changes over time, over the last 4,500 million years, yeah? So that is actually the point here, this dark point, which is called the Babi. That is the primordial value at 4,500 billion years, 4.5 billion years ago, to the present day, and the present day is here, yeah? Where is the present day? The present day is here at 0. There is the present day. So, and then you can collect your rock sample, and you can measure the 86 to 87 to 86 strontium ratio. Then you have the initial ratio, that is this ratio here of 0.7, something like this, yeah? And then you have the decay from rubidium to strontium. So, in this you can also measure and putting in this formula. So, you have the decay from rubidium 87 to strontium 87 that you can also measure, and you have the initial value of it is exactly 0.6999 initial value between 87 strontium and 86 strontium 4,500 million years ago, and you have the ratio today. And the ratio today is about 0.7 405. Yes, the value today is 0.7045, that you are adding just the value here of 0.027, yeah? That is here represented by the straight line. So, in the crustal rocks, which formed at about 3 billion years ago, they have another rubidium-strontium evolution, and there we have then a rubidium-strontium here of 0.15. So that you have to have in mind. So, but generally is, you have the initial rubidium-strontium ratio 4,540 million years ago. Then you can sample a rock, and you have the 87 strontium to 86 strontium ratio today, and then you have to add the decay or you have to your initial value, you have to add the decay from 87 rubidium to 86 strontium, using here the Eulersche function, and the half time, lambda is the half time there, of 40.8 million years minus 1, and then you are getting a value between the 0.699 and the 0.7045 for the value today, and then you have calculated the age. So, and therefore you can do the same with the isotope system from neodymium. You have neodymium 143 to 144. Then you have the ratio from neodymium 143 to 144, 4,500 million years ago. And you have the decay from samarium 147 to neodymium, which you can then calculate. So, and therefore you can use these values. Here, for example, we have here 3 figures. We have on the y-axis, we have always the neodymium 143 to 144 ratio. And on the y-axis, on the x-axis, we have 87 to 86 strontium, which has been calculated, yeah? So, and therefore, we have here, in picture number A, the fields from oceanic basalts, yeah? They have their a very low 87 to 86 strontium ratio of 0.70 up to 0.73. So because they are just formed very, very recent, yeah. So, and then we have the ocean island basalts, and they are showing a more wide range, yeah, because they are scattering more in age, yeah. So they are going up to 0.707. So that is this field for the ocean island basalt. So, and then we have the cross here inside, and that is then the one for the bulk earth, yeah. So then the next diagram is for subduction related basalts, and the subduction related basalts, they are scattering over the whole area on the subduction related basalts on the Iceland arcs, yeah. That means, and active continental margins like South America, yeah. So they can then also be used as petrogenetic indicators, which shows us, or which can give you some information from which geotectonic setting your rock has been formed, yeah. So, and then number C, we have the intracontinental plate basalts. So, and they are showing then another distribution field in their neodymium and strontium isotopic pattern. So now you would say why we are doing all this. I mean, when we are collecting a rock from the Andes, then it is a rock from the Andes, and we know there is an active continental margin, yeah. So, but as you know by now as well, our plates are moving always due to plate tectonic processes, and we have to reconstruct the position of all our continents in space and time, and to reconstruct the tectonic history, the plate tectonic history, and therefore we need these measurements, and therefore the afterwards the diagrams, to figure out how did it look like during Rodinia, or how was it during Gondwana at this and this place, and then we can reconstruct the Earth's history. So, and as you know, in geology we are always saying the past is the key to the present. Yeah, because it's always we are always repeating and repeating different processes which can or which will take place in millions of years scale. So, and of course we have a wide range of rubidium-strontium ratio of crustal rocks, incrustal rocks. In generally, the 87 strontium, 86 strontium ratios are much higher than those of the upper mantle. Yeah, therefore we are getting here higher values. Yeah, because we are adding then also on from the crustal side the decay from rubidium to strontium. So now we have here another diagram with the epsilon neodymium and the epsilon strontium. Yeah, we have here two formulas. Epsilon neodymium, we have 143 neodymium divided by 144 neodymium at initial. Yeah, then divided here by the Kur, and then we should know what the Kur is. And the Kur, that is the chondritic uniform reservoir. Yeah, so that these are the values for the chondrite. And then we can calculate the epsilon neodymium, and that is then the value ranging between 0 and here minus 40, yeah, depending if we are dealing with old crust or younger crust. Yeah, so the older crust has a higher negative epsilon neodymium. And then we can compare this with the epsilon strontium. You have also 87 strontium to 86 strontium for the initial, yeah, 4,540 million years ago. Then we have the time nowadays, the ratio, which is then the ratio here above, yeah, the variations here above. And then we can calculate here the epsilon strontium, which varies here between 0 initially and going here up in this diagram to 600. Yeah, so an epsilon strontium of 0 we had 4,540 million years ago. Yeah, that was this. So, and here at 0 we have here bulk Earth. So, and then we have here young crust, we have here the upper crust, we have here the old crust. The old crust, we are talking here about an age of 3 billion years ago, having then an epsilon neodymium of minus 30 and ranging here between 2 epsilon strontium, between 300 and more than 600, and before we are finding such values in the lower crust. So, and this is lines here, that is the upper crust. Yeah. So, and of course, when we are going here at a very to the bulk Earth, we do not have lower crust. Yeah, because there the new formed crust is very thin, and it's growing downwards by cooling, yeah? And this cooling process taken time. Here, for example, at 1 billion years ago, we have still young crust and a little bit lower crust, and the lower crust becomes then more and more with age. Yep. So then we have here another diagram that is the same as for the rubidium, radiogenic rubidium again. But here we are using the 143 neodymium to 144 neodymium. And on the x-axis we have again the age. Here we have on the right side we have now, that is present. And here we have 4,500 million years ago. Here we have the core and the bulk Earth, which is here the same, yeah. Then here we are forming then by partial melting or enrichment or an enrichment event, we are forming here the depleted mantle, yeah. And here we are forming the enriched mantle. So we are splitting this. That means the depleted mantle is then more shows then higher, 143 to 144 neodymium ratios, and the enriched mantle lower. So in the line here through that is the core respectively. Yeah, so you have always to figure out if you are doing with the dealing with the enriched mantle or the depleted mantle, and that you can find out by using different geochemical methods. So now we are going to the last radiogenic system which I will show you here in class. That is the uranium-lead system, yeah? So we have the decay from uranium-238 to uranium-234 and then to lead-206. Then we have the decay from uranium-235 to lead-207. And we have the decay from thorium-232 to lead-208. And all these ratios can be measured. So, and here in this curve, we can show the isotopic evolution of lead in the Earth. We have on the x-axis the ratio between 206 lead and 204 lead. So 206 lead is formed at first by the decay from uranium-238 to uranium-234, and then we have the lead-206, which we can analyze, yeah. So and then we have the lead-207, 204, and therefore I have written down the three equation. We have here the three equation for lead. The ratio for lead 206 to 204. The initial values, then we have the initial values from lead 207 to 204. And we have the initial values from lead 208 to lead 204. And here I have written down the initial values which they have calculated here. And therefore you can use the uranium-lead isotopes for age dating, and therefore a very famous mineral or the most prominent mineral which you can use for uranium-lead dating, that is the mineral zircon, which is in all felsic and intermediate and in some of the mafic rocks available. So, and then you have here the different geochrons at time 0, yeah, that is time 0 is here. Then you have 1 billion years ago, 2 billion years ago, 3 billion years ago, and you have the different mu ratios from uranium-238 to 204, and this can be used here for the uranium-lead dating. Or it can be used also for an petrogenic or geochemical indicator, yeah. For example, the Moore basalts very young, yeah. So therefore they are plotting in this field here the ocean island basalts, I mean, and the Morbs, which we can see here in the figure, in the first figure on the upper left corner. We have on the y-axis 207 lead to 204 lead, and on the x-axis we have everywhere 206 lead to 204 lead. So, and therefore we can use the lead isotopes as well for the identification of different for the identification from rock samples from different geotectonic settings at different times. Here we have it, for example, the Morb and the ocean island basalts. Here we have the continental rift zones and the continental flood basalts, yeah, scattering over a wide range. And here in this diagram we have the Iceland arcs and active continental margins, which showing lower ratios compared to the, or some of them showing lower ratios compared to OIP and to the intracontinental plate basalts. But the intracontinental plate basalts going here also to very low 206 lead to 204 lead ratios. So here we have now two chapters in one. So we have the variation of lead 207 to 206 lead versus 206 to 204 lead. So, and there we can use this also to subdivide the upper material from the upper crust and those from the lower crust, yeah. Works actually wonderful. And we have there an overlap for the oceanic sediments. So, but we have also other isotopic systems which we can use for the identification if a rock comes from probably from the lower mantle or from the upper mantle, or if it was hydrated, or if it was an oceanic basalt which becomes subducted and then hydrated. And therefore we can also use isotopic system, and a very important other isotopic system, that is these are the oxygen isotopes. And the oxygen isotopes oxygen can have three isotopes, that is oxygen 18, oxygen 16, oxygen 17. So, and therefore you can use this, and then we have to, you can analyze the oxygen isotopes, and then you can figure out if this oxygen was, or if you are analyzed minerals or rock sample have been in contact with oceanic water, or is it a pure mantle source, or whatever. And therefore we have at first to figure out what means SMO, the SMO, and the SMO value, that is the value for the standard mean ocean water. The standard mean ocean water, again, the standard mean ocean water is here, and here you have the oxygen 18 to oxygen 7 of your sample, and then you can calculate your delta or your oxygen isotope values, and then you can see how far it varies from your standard mean ocean water. Because the oxygen isotope or the isotopic ratio of oxygen in the Earth's mantle, in the lower mantle or upper mantle, is quite different from that one from the oceanic water. So now we are coming to some other classification diagrams. As in metamorphic petrology, we are using triangles also in igneous petrology, because we can use it for showing three components in space. So, and therefore we have now number 2.14. We have a tectonomagmatic discrimination diagram for basaltic rocks. So, and therefore we have at the top the titanium concentration divided by 100. Then at the left corner we have zircon, and on the right corner we have yttrium multiplied by 3. So, and then we have different geotectonic settings here in this, within the triangle. We have VPW, VPB, these are within plate basalts. Then we have IAT, these are the Iceland arc tolleites. Then we have CAB, these are the calc alkaline basalts. Then we have the MORB, these are the middle ocean rich basalts, and they have there everywhere a field, and you can just, when you have a rock sample found somewhere, and then you identify this sample as a basalt, then you can just start with the, you are making your analysis, and then you can plot this in all these variation diagrams, then you are getting a first impression in which geotectonic settings this rock has been formed. Then we have number 2, we have titanium oxide at the top. Then we have manganese oxide multiplied by 10 at the left corner, and we have apatite multiplied by 10, the apatite concentration multiplied by 10 at the right corner. So, and then we have OIT, that is the ocean island tolleite. Then we have OAI, that is the oceanic Iceland alkalic basalt. Then we have the MORB, the middle ocean rich basalt. IAT, that is the Iceland arc tolleite. And CAB, that is the Iceland arc calc alkaline basalt. So in the next diagram below, on the left side, we have we are plotting at the top 2 times neop. Then we have zircon divided by 4 in the left corner, and then we have yttrium at the right side. And we have the different fields here. For VPA, these are within plate alkalic basalts. Then we have the VPT, these are within plate tolleitic basalts. Then we have the VAB, these are volcanic arc basalts. Then we have the P-MORB, that is a plum morb, that is enriched compared to the N-MORB, which we will talk about in chapter number 5. And then we have the N-MORB, that is the normal morb, which you can find at the middle ocean ridges. So, and there you have then your different fields inside, and you can classify it. You can classify the rock which you have found in the field. Then we have here on the lower right hand, we have the hafnium concentration divided by 3 at the top. Then on the left corner we have thorium, and on the right corner we have tantal. Then we have the different fields inside. We have the N-morb, yeah? We have the P-morb, we have the Within plate basalts, and we have a destructive plate margin basalts, which are affected by crustal contamination. Yep. So, and that was it now for today. I will upload the videos, and tomorrow we are going to chapter number 3.